Thank you. That's my wife's working. Really? Wow. Okay. Which means I was in the weeks. Farmers sports secretary. Storm fish for the turtle. Yes. Oh, you're the wrong one. Alright, oh, we should do it.
Is that everything you need? Water?
Yeah.
Battery?
I imagine there's audio capture everywhere. I don't need to mute here.
Yeah, we're capturing here.
Okay. Do you need to allow me to share my screen?
I don't think so. Which is. One or two other people have experienced this issue.
Alexander, did you ever resolve the issue where Zoom not be shared?
There's no option whatsoever.
I see. Nothing.
It's my pleasure to introduce Dr. Littenberg, who's a research astrophysicist at NASA Marshall Space Flight Center, about an hour and a half away from here. He's also the lead scientist of the LISA Analysis Center. Effectively, he's the guy who's going to make sure that LISA can see all of the amazing sources that it's capable of and get us all that incredible scientific results. He's forgotten more about MCMC than many people actually know. So you're going to have a treat and learn a ton about advanced sampling methods. Let's give him a round of applause.
Thanks, everyone. Hi, everyone. I hope you're having a lovely 2 weeks. Is this the end of 2 weeks? I hope you have some energy left. So I was asked to talk a little bit about advanced sampling methods. So you've learned a little bit about MCMC already. MCMC is really the gateway drug to this broad world of Bayesian stochastic sampling algorithms. It's still also my favorite one. But we'll talk about some of the other algorithms, why they're good, what sort of pitfalls they have, and maybe tempt you to try some of them out in the future. But since I think for some of you, MCMC is a new concept, it was covered well earlier in the week, but I just want to make sure that we're all level set on the same page and at least make sure that you understand the notation that I'm using in case it doesn't match the notation you've seen already. So we'll start with this. This is the central engine of everything that we're doing. This is Bayes' theorem, which tells us how the posterior distribution function, the thing on the left, which is the probability distribution of, in our case, say the model parameters that we're using to describe the data, capital D, relates to the right-hand side, which shows the likelihood, that's the probability that our model and our parameters predict the data that we've observed, times the probability that we thought our model parameters would take before we collected any data, and then it has that annoying normalization term on the bottom. So when you saw Bayes' theorem earlier, you might not have had the comma M there on the conditional side of the probability. Is that possible? Maybe it just said theta D, okay. I see one of our lecturers in the back nodding vigorously. So remember, in these conditional probabilities, anything to the right-hand side of the vertical bar is the thing that you assume is true. And in the shorter way of writing Bayes' theorem, where the posterior would just be like P of theta bar D and then end of parentheses, what you're implicitly assuming is that the model you're using to describe the data is true. And all you care about is how do your parameters for that model fit the data. What I'm going to do is I'm going to be more explicit about including the model on the right-hand side of the conditional probabilities for two reasons. One, to remind you that everything you're doing depends on the fact that the model that you started off with was a good model. If the model you started off with was a crap model, Bayes' theorem will not save you. It will just give you very confident answers for a very bad model, okay? It will Bayes explain to you how your parameters fit the data. And the other reason I want to include it up there is because one of the things that we want to talk about today is comparing different models of the data using the same engine. And so it'll be handy to have it up there in all the conditional probabilities. All right, so we're cool with Bayes' theorem. And then we talked about MCMC, which takes Bayes' theorem, does some manipulating of it, and then tries ways of randomly exploring parameter space, and then uses some sort of fudge factors to fix how you're exploring parameter space to come up with this thing called the Hastings ratio, or the acceptance probability. And that looks like that. So do we remember seeing that? The left-hand side of that is Bayes' theorem again, but now for comparing the posterior distribution function for a proposed set of parameters, we're going to call them theta prime, and comparing them to our current set of parameters, we're going to call them just theta. So that highlighted in red ratio is the posterior distribution function at theta prime in the numerator and at theta in the denominator. And because that normalization piece in the bottom does not depend on the model parameters, it just cancels out. So the left-hand, the red highlighted part is basically the posterior distribution, the relative posterior distribution between two places in parameter space. And then the part highlighted in blue is there to counteract how you've tried exploring around parameter space. So if you push really, really hard in one direction in parameter space, this ratio is going to push back in the other. I describe it like a teenager. The more you want a teenager to do something that you want it to do, the more it will push back. I have teenagers at home. It's very relevant. Okay, so you use that algorithm, and within a model that you have with some model parameters, you can explore the space, and then you can come up with FAIR draws samples from this posterior distribution function, and then you can use those samples to learn about the distribution. You can calculate moments if you're into that. You can say what's the mean, what's the variance. You can just report them as a big table. You can make corner plots, all that jazz stuff you've probably all been working on for the last 2 weeks. Okay, but now let's talk about that normalization piece a little bit. Does anybody remember what that's called? A particular kind of likelihood? The marginalized likelihood, and the other name for it is the evidence. Okay, so what does marginalized mean? Marginalized means you did an integral. So what did you do the integral over? Parameter space. Okay, so you take the posterior, just the likelihood times the prior, and you integrate up over all of parameter space, and then you get that thing. So if you're just talking about within a model, it's an annoying normalization factor. You have to do this big integral, but look, it's a probability of data given a model. That's a likelihood. That's a measure of how well a model fits the data, not how well these parameters of a model fits the data, which is what you're doing when you're just doing an MCMC. This tells you how well the overall model is able to fit the data when you try out all the different parameter combinations. So this is a really powerful tool to decide if you're adequately representing the data with the model that you started with. Okay, so there it is. So to calculate that thing, you do this big integral over all of parameter space of your likelihood times your prior. Easier said than done. So the trick here is that in interesting problems, the dimension is large, and big, high dimension integrals are really, really hard to do. So this machinery, this Bayesian stochastic machinery, can also be used to do these big integrals for you, instead of trying to find some other numerical integration scheme over this large dimension parameter space. Okay, so one that we're going to talk about is one called nested sampling. Have we talked about nested sampling at all these last 2 weeks? A little bit. Some say no. Okay, cool. So nested sampling was designed to take all the nice parts about this Bayesian stochastic sampling and say, I don't actually care about the parameters. All I care about is this evidence thing. All I care about is the marginalized likelihood. So I'm going to find a way to conveniently marginalize over those nuisance parameters that do things like describe how well my model fits the data. I just want to know if it's a good model or not. And the way we're going to do that is we're going to take this really high dimensional integral, and then we're going to do some clever things to squash it down into one dimension. And so we're going to write it this way, where we're going to use capital Z as the evidence. And then to calculate the evidence, we're going to do this integral over the likelihood, just capital L. And then this volume element, which instead of being d theta, we're going to write as the prior times d theta. Okay, now we all know that there are a lot of dimensions packed into the way we've written this equation, but this is how we're going to sort of bootstrap our way. So now take a leap of faith with me. We're going to define this parameter x as, I think there are words that come up next. Yes, as the cumulant prior mass covering all likelihood values greater than lambda, which is a mouthful. What it really is the volume of the overall prior for which the likelihood value is greater than some value lambda, okay? So as lambda gets big, as the likelihood value gets big, what's going to happen to x? No problem, we're going to start over again. So x is the volume of the entire prior where the likelihood is greater than lambda. So as lambda gets bigger and bigger, that means the likelihood's getting bigger and bigger. So what's going to happen to x? It's going to get smaller, right? X will get smaller and smaller as lambda gets bigger and bigger because a smaller fraction of the prior has high likelihood values, okay? Great. So that means that the bounds of this integral are just from 0 to 1, where 0 is when lambda is very, very large. That means the likelihood is large. That means it's a very tiny part of the overall prior volume where you satisfy this condition. And lambda is 1 when the likelihood is really small. That means you're covering the whole prior range. So we can turn this into a one-dimensional integral with really simple bounds just from 0 to 1. Okay, this is something that a computer is going to like to do. Okay, the other thing that's really, really handy for doing this numerical integral is that this function L of x is always positive and will monotonically go down as we go from x equals 0 to x equals 1. As I get to more and more prior volume, the likelihood will get smaller and smaller and smaller. And so we can sort of bootstrap our way going backwards. We can start with a very large volume, okay, so it's covering most prior, that's shown in red there, and that's going to have some value of likelihood, some value for which all of the samples have a higher likelihood than that. And then if I shrink that space, then this function is going to go up a little bit. And if I keep shrinking, it keeps going up until eventually I get to the maximum likelihood region and the minimum prior region. Okay? That function, that red curve there with L3, L2, L1 is really, really easy to integrate numerically. You could just do your favorite like Simpson's rule or whatever integral to do that. And that function gives you the evidence. The area under that curve is the evidence. So this nested sampling algorithm is basically designed to shrink the contours in parameter space and accumulate the evidence as those contours shrink as you go. Okay, so here is the algorithm in just a few words. So you start off with some large number of samples and you just sprinkle them all over the prior. And that's your starting position. And you assume that the evidence here is 0 because this is the first point in the curve that you're trying to integrate. And you assume that this value x is 1 because you've covered the entire prior. Okay, and then you calculate the likelihood for every single point that you've sprinkled all over the prior, and you find the one with the worst likelihood. That's going to define sort of this outer, do I have a pointer? Do I have a stick?
It is a pointer out there.
Ah. Yeah, so you find the one with the worst likelihood, and that's basically going to define where this outermost contour is, okay? And then you trust in fate and say, I'm just going to say that the contribution to the evidence is something like this e to the minus I over n. I is the iteration you are in this algorithm, and n is the total number of samples that you work with. And there's a long and unsatisfying argument as to why this is a not bad idea. But then you can then estimate what the evidence is contained within that shell using this simple expression here. And then take that point that was bad, that was the lowest value of likelihood, and resample the prior until it has a higher value of likelihood than it did before, which is really easy at the beginning of the algorithm because your points are scattered all over the place. This gets more complicated as you get later and later into the number of iterations you're doing. But what you've basically done is shrunk the space where these samples are living. And then you repeat this over and over and over again until some convergence criteria is met. Okay, the some convergence criteria met is usually that your evidence stops growing. So you do another iteration and the evidence doesn't really change. That just basically means you're not shrinking the contours anymore. And lo and behold, what you end up with is the overall evidence for your model, the marginalized likelihood for your model. Okay, so now if you have another model that you care about, you can repeat this process for that other model you want to try, and you can compare these numbers. The in vogue way to compare them is to take the ratio, and what's it called when you take the ratio of these types of numbers? It's called the Bayes factor. Yeah, the Bayes factor, which is the likelihood ratio of model A versus model B. Okay, does a higher Bayes factor mean it's a better model? Why not?
Could be indicative that your model is just kind of telling you what you want it to say. Makes sense?
A little.
I think very high base there, things that are not true.
Let's guide the audience here a little bit and go back to this one. So if you have a high value of likelihood for theta prime, does that mean it's better than theta in just the fixed dimension case? Why not? Because there's that prior thing outside, right? So just because it's a better fit doesn't mean it's better. because you might have really good reasons to believe from an earlier experiment that theta is actually a better value than theta prime. Let's say one experiment went and measured, I don't know, a stochastic background of gravitational waves using pulsar timing, and then a different experiment using different pulsars and using different radio telescopes also does a measurement, and they disagree a little bit, okay? So the measurement you did before, you don't just throw out and just take only the likelihood, you let what you learned before help influence the result. That's the magic of using this Bayesian machinery. So the same argument goes for this model selection game. Just because you have a Bayes factor that's greater than 1 doesn't mean that's a better model. You have to also consider whether or not you think one model is a better argument over another. So let's take a wild example. Let's say the LIGO-Virgo-Kagra collaboration has measured something like 1,000 binary black hole mergers at this point and is pretty confident that they're all pretty well described by general relativity. And let's say there's one binary black hole merger where they do a model selection test and it says, oh, this one looks like it's slightly different than general relativity, Nobel Prize, or reconcile the fact that this one doesn't work, but the other 999 did. And so you need more evidence, you need more of a stronger likelihood ratio to convince you that this one is doing something different than the other 999. Okay. Great. Now, the downside of all this is that you went through all this trouble to calculate the likelihood, but then someone says, well, do you have like a cool corner plot you can show? Because I like the corner plots that tell me about the parameters. And you don't have samples from the posterior distribution function by doing this algorithm like you did with MCMC. Remember, MCMC goes through all this trouble of detailed balance. So as you're updating the parameters, you're satisfying the statistical condition so that the new step doesn't depend on the old step. In this algorithm, we're forcing the parameters to get tighter and tighter, we're forcing the samples to get closer and closer together. So the samples that you have do not represent the posterior distribution function. However, you know what that pesky normalization term is in the overall Bayes factor. So you can take the evidence that you have, and then you can go back through all the samples that you use to calculate the evidence along the way and re-weight them to come up with a representative sample of the posterior distribution function. So if you're using MCMC to do parameter estimation, and then you want to do some model selection, you have to do like additional things to come up with the evidence. Nested sampling goes the other way around, where it says calculate the evidence first, and then do some post-processing to come up with estimates for the parameters. So if the problem you're trying to solve is really, I don't care about the parameters, I care about the model, maybe you want to jump into nested sampling. If the problem you want to solve is, I really want to measure the parameters and then maybe do some model selection, maybe you want to start with something like MCMC. So it depends on what your priority is when you're trying to decide between these types of algorithms. Okay. Now this idea of having all these parameters sprinkled all over parameter space, all over the prior, and then making use of them to do calculations helped spawn a sort of happy medium algorithm that takes the nice things about nested sampling. One of the nice things about nested sampling is it's very, very parallelizable because you're calculating likelihoods of many points all at once, whereas MCMC is strictly serial. You do one point and then the next point and then the next point. So it's hard to jam an MCMC onto modern computers that like to do lots of work all at once, but nested sampling really lends itself to being parallelized. So let's try to find a happy medium. And one happy medium is this idea called ensemble sampling. And this has really taken over the universe, partly for good and partly for evil. So ensemble sampling is this idea that we want to generate samples that are representative of this posterior distribution function. So here's an example of posterior distribution function in different shades of blue. And then there's just like a single point in there in parameter space X. And remember, like I just said, MCMC is serial. So you start off with a position X, and then you move to another spot, calculate likelihoods, make some choices, try out another spot, try out another spot, etc. This is hard to parallelize. You can do the nested sampling thing where you just sprinkle samples all over space. You can calculate all those likelihoods in parallel, nice and efficient, and then force them to get closer and closer together around the maximum value. Okay, very parallelizable, but not a representative sample of the posterior. So then you have to do this extra processing afterwards to do parameter estimation. So ensemble sampling tries to find a happy medium between the two. So you start off with parameters that are just sprinkled, or sorry, samples that are just sprinkled all over parameter space. And the jargon du jour is to call each one of those samples a walker, because it is going to walk around parameter space and try out different values. And then you do a clever thing, which is say, I have a whole bunch of walkers sprinkled all over parameter space. I'm going to take some of them and I'm going to hold them fixed. And then I'm going to use where they are in parameter space relative to others to decide how I'm going to jump or update the parameter values for the other walker. So let's take this pair, for example. So let's say I'm going to hold this one fixed, the one that's a little bit lighter, and then I'm going to pair it up with this one. You can connect a vector from this walker to that walker. And then you can say, I'm just going to draw a random number that is like an amplitude along that vector. And that's going to send this parameter maybe a little bit, or this walker maybe a little bit inward or maybe a little bit outward. And then I can do my Metropolis Hastings algorithm to decide if I want to accept that move or not. The handy thing about this is that once all of your walkers are fairly representing the posterior, you're going to naturally propose moves along like principal components of this error ellipse. Because if you just pick a random walker and hold it steady, and then pick another random walker and try to update it, odds are it's going to be along a correlated direction. So even if you've done a bad job of parameterizing your model, and if you're just doing vanilla MCMC, you have to think carefully about what directions to do your proposals. This ensemble sampling scheme sort of figures that out for you. And then there are other things you can do to juice it to make it even more efficient in its sampling. Okay, so yeah, so you will update some of the walkers based on the location of other walkers, and then you can sort of go A side, B side, and you can keep the updated walkers steady, and the previous one that were held fixed, they all get updated, and you can rinse and repeat this a couple of times. And then the really nice thing about all this is, let's say you have 1,000 walkers, why not? And you do this iteration, this process a couple of times so that everything is converged. The 1,000 walkers at any moment in the algorithm should be a fair draw of the posterior. So unlike MCMC, where you have to do 1,000 steps to get to 1,000 draws of the posterior, modulo having to thin them because of correlation. If you do this ensemble sampling scheme, if you have 1,000 walkers, you only really need a few iterations, and then you have 1,000 draws from the posterior. So it can be very efficient. And that is why it has taken over the universe. Not only is it an efficient algorithm, but it plays nice with modern computers. So there are at least two, probably several other common Python packages for doing this. One's called MC, that was sort of the original gangster version of an ensemble sampler. And then there's another called Aaron, which is optimized for using GPUs. And these are really handy, I will say, with an asterisk, if the sampling part of your problem is not particularly interesting. So if it's a relatively small parameter space, if it's a relatively simple parameter space to explore, you just want someone to give you a nice looking corner plot without thinking too hard, then just pip install these and use them. But if you have a large dimension parameter space, this starts to get pretty fraught, because let's think the extreme case. Let's say you have a 3-dimensional parameter space and you only have 2 walkers. Those 2 walkers will explore a plane in an otherwise 3-dimensional parameter space. So as the parameter space gets larger in dimension, the number of walkers you have to use also has to get larger in dimension, and you want way more walkers than you have dimensions. Okay, the case where you have like 3 walkers for 3 dimensions is not very efficient. Does anyone know what the rule of thumb is? There's a rule of thumb. It's like two times the number of dimensions, right? So, okay, whatever. If I have a 5-dimensional parameter space, 10 walkers, no big deal. If you're talking like the Lisa global fit, for example, where you have something like 100,000 parameters, this is starting to look problematic. Okay, there are also, for all of these algorithms, you can design like sort of pathologically shaped distributions where these type of algorithms struggle. So the beauty of an ensemble sampler is that you don't have to use any domain knowledge. You don't have to know what you're looking for, and the ensemble sampler will figure it out for you, as long as what you're looking for is not too complicated. If what you're looking for is high dimension or has some really funny shapes to it, and you have to start force feeding how your walkers update to explore that whole space, you're well on your way to writing an MCMC at this point anyway. So there's a balance to be struck. Okay. The other new kid on the block, which is really cool, is this technique called a Hamiltonian Monte Carlo, or HMC. These are rad. So here's what we're going to do. Instead of trying to devise clever proposal distributions, instead of trying to use these ensemble samplers to learn the proposal distributions for us, we're going to reach all the way back to when we took classical mechanics and use Hamiltonian dynamics to do this hard stuff for us. So we have already defined a bunch of parameters x. Okay, so in like a Hamiltonian sort of sense, you can think of those as positions. Okay, and we've already defined our posterior distribution function, which is proportional to the likelihood times the prior. And the whole idea of these sorts of algorithms is to try to find the top of this hill of this posterior distribution function, and then do a good job of sampling the space around it. We're going to literally flip that on its head, and we're going to, instead of think about a hill, turn this into a well, like a potential well that we need to explore. So we're going to define a potential, which is the negative log of the unnormalized posterior distribution. Why log? Because logs numbers are smaller and easier for computers to deal with. Why negative? Because we want it to be a potential well that we want to be stuck in instead of a hill that we're trying to roll over. So we flip the sign on this so that it's a hole instead of a peak, and we take the log of it so that the computer is happier, and we call that our potential. Okay, now if you're going to do Hamiltonian dynamics, what's the other thing you need? You also need momenta. So what I'm going to do is I'm just going to poof into existence the idea of some momentum. And if you now go way back, remember that the kinetic energy is the momentum divided by 2 times the mass in just like a single, classical mechanics problem. To map that to what we're trying to do, we're going to say our kinetic energy for our momentum vector is the product of our momentum vector with this thing called the mass matrix. Okay, so this is like the multivariate version of that. Okay, this should look familiar from classical mechanics. This might not look familiar from classical mechanics, but it's the same thing. So now that I've defined this, this kinetic energy, and I have some potential energy, I can write down the Hamiltonian as the sum of those 2 things. And then remember that our Hamiltonian is now the potential part depends on our model parameters and is like our posterior distribution function. And the kinetic energy part is the momentum, which we haven't really defined yet. We just said it exists. And this mass matrix thing, which is probably currently a little bit mysterious. But with this machinery, I can just solve Hamilton's equations. So changes in the position depend on derivatives of the Hamiltonian with respect to the momenta, and changes in the momenta depend on changes in the Hamiltonian with respect to the positions. So now I have these coupled equations, and people have been solving Hamilton's equations on supercomputers for a very, very long time. So there are lots of oiled machinery for doing these types of numerical analyses. And so we're just going to hijack that and use it for our parameter estimation purposes. Let's see. So the downside is that this requires calculating derivatives of the Hamiltonian, and that means calculating derivatives of our posterior distribution function, and that can be pretty expensive. Okay, unless you have a rather trivial looking equation, it's hard to just write down analytically what these derivatives would be. So you either have to do a bunch of finite differencing inside of your algorithm, which is costly, or you can use really snazzy modern programming languages that can figure out derivatives for you just based on how you write the functions. But then the secret sauce here, the secret sauce here is how you define this, this mass matrix. So this is basically how hard you're going to kick your sample in this parameter space. So I'm going to kick the sample, and then I'm going to numerically solve Hamilton's equations, and it's going to just roll around inside of this posterior. And then I'm gonna kick it again and it's gonna roll around, and then I'm gonna kick it again and it's gonna roll around. And I evolve it for a certain number of steps, that's up to you. And where it lands, that's basically like a really good proposal. And then I can use where it ends up at the end of this evolution to decide whether or not I want to keep that sample just like I do with MCMC, which is a mouthful to describe. But Wikipedia made a really nice animation for this, so we're just going to use it, okay? So here's this funny shaped distribution that you're trying to sample. Here's the starting point, and now with this mass matrix that you just get to make up, this is where the art comes in as well as the science, just like you're making up proposal distributions in MCMC. You just give it a kick, and then you watch it roll around, and then you kick it again, and evolve for a while, and then kick it again, and then evolve for a while. And this can be an extremely efficient way to make big moves in parameter space, especially in these really funny shape distributions. So we can just be mesmerized and watch this little particle roll around. There's one extra piece of frosting that you can put on this algorithm called a no U-turn sampler, or NUTS, which keeps track of the trajectory. And if it notices that the particle has like turned back around and is coming back from where you kicked it, it stops. All right, so the idea is if you've gotten really, really far away in parameter space and then you start to roll back, stop the evolution there and then just take where you are far away because you want to really efficiently sample this larger space. And it's up to you to decide how long you let this thing evolve before you do the Hastings ratio evaluation. So HMC is super rad. The hard part is that it requires being able to take derivatives of the likelihood. That's tricky. The other hard part is that it's really stuck in one dimension. Okay, it's hard to imagine doing this, not one dimension, but one model. It's really hard to imagine doing this between different models. And we also care about model selection. So what we're going to talk about, I think now, is my bread and butter, which is using these sampling algorithms to actually try out different models. Is there a question in the back?
Yeah. How to go about using the matrix?
Yep. So the sort of naive implementation is literally guess and check, which is using an adaptive scheme. So you start off just, I don't know, whatever, some multivariate Gaussian, and then try to learn what a efficient mass matrix is as the algorithm goes. You can imagine things that you would develop for the purpose of doing efficient MCMC exploration would also make good mass matrices. It's basically your proposal distribution. So something like a Fisher information matrix is also like a good place to start once you're sort of rolling around inside of the main part of the posterior distribution. But that's the mass matrix part. That's the special sauce. That's what you have to think about. And that's where the domain expertise comes in. So I would say HMC is less plug and play than an ensemble sampler, but it can be really, really fast if you plug and play it right.
Are we defining the momentum as the gradients of the parameter in their space, or are they a different thing?
Different thing. We just need the concept of a momentum in order to use this machinery of the Hamiltonian. So we're just going to poof into existence that these momenta exist. It's a vector that has the same dimension as the positions. And then our momenta and positions are just like paired, like conjugate pairs to move around just like they are in classical mechanics.
Are they chosen based on the prior, or are they just chosen one?
They're not chosen at all. It's a device to use to update, let's see. I don't have it explicitly written out. But here we go. So you just use this little mass matrix to start the momentum moving. And then you can iteratively solve these differential equations to figure out how much your positions have changed. Okay. And then do the Hastings ratio thing to decide whether or not you want to accept those new positions. And then with that, kick them again using that mass matrix again.
Like the version, pick the back.
Yeah.
Done. Thank you.
Okay.
Yeah, I'm curious about The motivation for that is everything that you currently back. Well, good.
If your goal is to find the peak, then I understand the motivation, but the goal is not to find the peak. The goal is to explore the space so that you have a representative set of samples from the whole distribution, right? So if you just wanted to use this as like a hill climber to sink to the bottom of that well, you would come up with a different algorithm, but still make use of all this different machinery. But we don't just care about the peak. We want to know what the shape of the distribution is, including the peak. Okay. Cool. Enough of that stuff. Now we're going to talk about my favorite thing. I've somehow managed to make a career out of this, called transdimensional sampling. It is also referred to as reversible jump Markov chain Monte Carlo, or RJMCMC. It's a terrible name, but it's stuck. So we'll call it RJMCMC. The name does not immediately invoke the idea that you're changing the dimension, whereas transdimensional sampling does. I didn't name these things. I'm just stuck with it. So we've talked about sampling algorithms within a model. So here is a toy example of some model space M with some parameterization X, and you just have your places in parameter space updating according to our Bayesian stochastic sampling rules. Now, let's imagine a simple case where you're trying to fit features to data, and you're trying to decide if you have one feature or two. So this could be like bumps in a spectra. This could be like individual sources, individual gravitational wave sources in some pulsar timing data. This could be a variety of other things. But let's pretend the question is, do I have one thing or two things that I'm trying to fit? Arguably, those are different models. One model has just one thing in it, and one model has two things in it. So they have different dimension, they're different models. And you can use this machinery to then say, well, I can, just like I can use stochastic sampling to move around inside of a model, I can also use stochastic sampling to try out different models, say one feature or two features, and have all of the nice statistical rigor behind it, so that what I end up with is a posterior distribution function in model space, not just a posterior distribution function in parameter space. So if I have just two models, then I can just use this stochastic sampling to try out model A and model B and move back and forth between them with the same detailed balance rules that I have within the model. And then I can say, let's say I did 1,000 steps in my algorithm. If 500 of the steps were in model 2 and 500 of the steps were in model 1, that means those models have equal likelihood. So equal Bayes factor, a Bayes factor of 1 between those two models. And then maybe you have some prior that tilts the scales one way or the other. Okay, so let's break it down looking at the equations instead of just a poorly drawn picture. So let's imagine a really simple case where you have a single parameter model theta, and then you want to test whether or not an additional parameter phi does a better job of fitting your data. Yes?
The first part about adding in parameters, does it always have to include the previous parameter? Like, for example, your data and data phi. So
Right.
when comparing models, it has to include like the previous parameters of the previous model.
Right. It does not. So this case where the previous model is contained within the trial model is a special case where they're called nested models, where one model lives inside of the other. These are the easiest ones, and for most applications that we face in gravitational wave astrophysics, I think almost always applicable. Almost, maybe doing a lot of work there. So we'll just stick with the nested model case, but it is not a requirement. You could just have completely disjoint models that you're trying to use. Okay, so we're going to go back to our friend, the acceptance probability, the Hastings ratio. And so here we have, remember, the likelihood at theta prime, the new values times the prior at theta prime, and then this ratio of proposal distributions to see how you go from one to the other. Okay, so that's the within model case. And now, if we're going to say, now I have my current location is that I'm just using a single parameter theta. and my trial location is that I'm going to use two parameters, theta and phi, then the numerator now has theta and phi as part of the parameters. So that involves the likelihood and the prior. The denominator is where I am, just a single parameter theta. And then remember, the proposal distribution is flipped on its head. So the proposal distribution in the bottom has that extra parameter in the denominator, and the proposal distribution in the numerator has the extra parameter on the conditional side. Okay? That's it. That's all we had to do. We just took the acceptance probability that like we had done before and just figured out where to put that extra model parameter, and then we're done. And just shove this into the computer and make it go. Not a big deal. So we're gonna make this a little bit easier to read so that we can get some intuition out of it. So now what we're gonna do is we're gonna assume that theta and phi are completely independent, okay? So the first example that I ever worked on for this was thinking about white dwarf binaries as observed by Lisa. White dwarf binaries as observed by Lisa are mostly monochromatic signals. They're basically at the same frequency. The orbital period is basically constant during the whole time Lisa is observing. Some of them will be orbiting around each other fast enough, or will be transferring mass from one to the other enough that you'll see some evolution in the orbital period. And so the question we studied like a gazillion years ago was, when can you measure a derivative of the orbital period? So we had our model that just said a fixed orbital period. That was like the theta version. And then we had an additional parameter, which is a first derivative of that orbital period. And we're going to see what are the circumstances where you can actually measure that first derivative. So in that case, these things are basically independent of one another. And so what I can do if they're independent of one another is, so I can take the likelihood, the prior, and the prior of theta and phi, if theta and phi are independent, is the prior of theta times the prior of phi. Geez, does that make sense? If I have a probability distribution and it has two parameters, but those parameters are independent, then it is the same as the product of their probabilities. I think we went over that when we talked about Bayes' theorem in the first place. Okay, so I can bust that prior up into two. Now, if my proposal here is to just poof a value of phi into existence, then the probability of deleting that value of phi, if I wanted to go back to the single parameter model, is 1. There's only one way to delete something, to delete it, okay? And then if these things are really independent, then if I'm going to poof a phi into existence, then it has nothing to do with theta. I just have a distribution that I'm going to use to try out new values of phi. And so the proposal distribution at the bottom just depends on phi. Okay, so the prior gets busted up, and this proposal ratio gets really simple. It's just 1 over how I generated my trial values for phi. Aha, look at these. Those are the same. Those are going to cancel. Sweet. Okay, so now I have the likelihood ratio between my more complex model and my simpler model. I have the prior of my more complex model, and I have the proposal of my more complex model, and that's it. That's the Hastings ratio. Okay, this looks actually kind of simpler than just a straight up MCMC. Okay, I think there's one more thing that we're going to do here. Nope, in a minute, to develop some intuition. So first, let's talk about some more interesting examples than just whether or not we want to add an extra parameter to a model. So here is some real life LIGO, Virgo, Kagra data back from the first observing run, way back when, 10, 11 years ago. On the left is a really exciting event that happened back then called GW 150914. It was the first ever observation of gravitational waves. It was a black hole merger, and this is the whitened time series of the black hole merger as observed by the Hanford Observatory, the one in Washington State. So it looks like a black hole merger. It starts off low amplitude, low frequency. It gets to high amplitude and high frequency, and then it goes away. And then there's some noise on top of it. On the right-hand side is not a gravitational wave signal. This is just a noise transient or a glitch. It's just the detector going bump in the night in the Hanford Observatory during that same observing campaign. The trick is that the search methods that find this also do a good job of finding this. And so how do you teach the computer that this is not a gravitational wave and this is a gravitational wave? There are a bunch of things you can do, but one of the things you can do is use Bayesian model selection. Okay. Even worse, sometimes they happen at the same time. So here is an example of some data during the second observing run. If you know your GPS times, this is a really important time. This is the 170817. This is the binary neutron star merger that was observed during the second observing run and also had a counterpart gamma ray burst. They found the host galaxy. Everybody on the planet wrote these papers. You might have been an author on these papers, whether you know it or not. It was a big deal. The signal in Livingston, the gravitational wave signal, you can tell if you know what you're looking for. It's this track right here is this binary neutron star signal. And then it just so happened to sit on this massive noise transient, this massively loud glitch at the same time. And this actually screwed up the whole mechanism of getting the alert out to the EM community and doing the follow-up to try to find the host galaxy, because the Livingston data was basically vetoed because there was this giant glitch sitting right on top of that signal. So what we need is some machinery so we can sort between the gravitational wave part and the instrument noise part in a nice, reliable way so that we don't veto these kinds of data and we don't bias our results when signals might be contaminated by noise transients. So we're going to build a likelihood function to take care of all of this. Okay, so let's build a likelihood function. To build a likelihood function, you have to make a bunch of assumptions. These standard likelihood assumptions for things like gravitational wave astrophysics are things like the noise is Gaussian with zero mean. We know what the variance is, so we can characterize it by something like the power spectral density. We have perfectly calibrated data. We know what we're looking for. We have really good waveforms. And the noise statistics yesterday are going to be the same as the noise statistics today, are going to be the same as the noise statistics tomorrow. And so once I write down my PSD, I'm done. Okay, those are 5 really important assumptions that we make about the data. All 5 of them are wrong. So here's a LIGO Virgo Kagra example. Here are a bunch of noise transients. Okay, so clearly the noise is not stationary. Here are the power spectral densities for the LIGO Hanford and LIGO Livingston. I'm going to guess during O2. And I don't know if you can tell, but there are some error bars on them. There's like a blue envelope around the Livingston curve and a red envelope around the Hanford curve. And that's because the noise is fluctuating over the course of the observing run. So the noise is clearly not stationary. We know the data aren't perfectly calibrated because every couple of months during these observing runs, they send out new calibration files. So clearly it's a work in progress. And of course the waveforms aren't perfect. Come on, there's definitely something wrong in the waveforms. We just haven't figured it out yet. Okay, so instead of relying on all of those assumptions, there was a motto going around, which was to just model everything and let the data sort it out. This is I would say, a little terse. And so the more verbose motto is to choose a convenient basis set to phenomenologically model features in the data and then use the Bayesian evidence to determine the number of these basis functions that you need to use in the model. So what we're going to do is we're going to come up with a very broad way of parameterizing anything that might happen in the data. Now you're worried about over-parameterizing and overfitting, and then we're going to come in with Bayesian model selection as a hammer to make sure that we don't use too many parameters and trick ourselves into thinking something cool is happening in the data when it's just because we've overfit it. All right, so we'll start with the noise. Here is a narrow segment of real life LIGO noise. I don't remember if it's Hanford or Livingston. So this is going from 60 hertz to 200 hertz. You'll notice some features. One in particular, there's this really big spike at 60 hertz that's always there. Can anyone think of why there's a big spike in the LIGO data at 60 hertz that's always there? Because what? Nope. Nope. It's plugged into the wall. Yeah. Yeah, it's on the power grid. The power grid in the US is at 60 hertz. In Italy, where Virgo is, it's at a different frequency. Their peak is at like 50 hertz. Okay, so that's because LIGO's plugged into the wall. Then you have some other spikes that come from just resonances within the big complicated detector. So you have these spiky features all over the place. And then sitting underneath them, you have this broadband noise that you might characterize by a power spectral density. Okay, so the features that we're going to need to build a parameterized model are to deal with these narrow band spectral features and then this broadband noise That's basically what's happening when you don't have one of these narrow lines. Okay, so there's actually a good reason to model the spectral lines as Lorentzians. The good reason is that they are damped-driven oscillators, right? Something is forcing the detector to jiggle at this particular frequency, but then lots of other forces are conspiring to keep it from jiggling. And it turns out that the Fourier transform of a damped-driven oscillator is something like a Lorentzian. So that seems like a convenient basis function to build a model for these spectral lines. For the broadband part, we went back and forth. You could try to use some sort of physical model, or you could just say, the heck with it. It's just going to be completely phenomenological. We're just going to fit it with a cubic spline interpolation. And then our parameters are going to be where the spline points are that we're going to interpolate between. So I am free to choose how many of these nodes I have and where they are in frequency and amplitude space. And then I'm going to interpolate between them to fit the broadband part of the noise. Okay, so then the model selection part is how many of these Lorentzians do you have in the fit? And how many of these spline nodes do you have in the fit? And then the parameter estimation part is what are the parameters of those Lorentzians and where are those nodes in the interpolation? Okay, so that should take care of the fact that we have an unknown variance in the noise. We'll wave our hands and say this is good enough for the non-stationarity as long as we use short enough strides of data. Okay, if I do this algorithm on data today, it won't be good enough tomorrow. But if I do this algorithm on data today, it'll be good enough like a few minutes from now. So you can use sufficiently short strides of data and sort of gloss over this non-stationarity as long as you understand the timescales of the non-stationarity well enough. Okay. Now here's some more data. Now this is a time series instead of a spectra. And so you can see it's noisy, and then there's like something that happens, and then it's noisy again. This happens to be one of these glitches, not a gravitational wave signal, but to a gravitational wave search, it looks very, very tempting. So what sort of features does it have? It is compact in time. It doesn't last very long. And it's compact in frequency, and you can tell because it just looks like a wiggle, okay? So we want a basis function that is both compact in time and compact in frequency, and a convenient basis function for that is a sine Gaussian. A sine is compact in frequency, it has just a single frequency, and then you put a Gaussian envelope to make it be compact in time, okay? So I'm gonna model my short duration transients like glitches or gravitational wave signals as a combination of sine Gaussian functions. Sine Gaussians, we're going to call them wavelets for short. They're technically not wavelets, but that's okay. The whole idea of wavelets is little compact time frequency wiggles, okay? So this particular one, if I just take this green sine Gaussian and this purple sine Gaussian and I add them together, I actually do a pretty good job of representing that glitch. So this took only 2 basis functions. Okay, so there you are, you add them up together, and it does a pretty good job of fitting the transient. Okay, so now that I have this, this wavelet model, I can take care of the fact that we have non-Gaussian features in the data. So now we're doing really well. Now we just have like 2 crummy assumptions left. And the last one we're going to deal with is that we have perfect gravitational wave models. So here's the data that contains GW1500914 again. So that's a binary black hole merger. You can sort of see it there if you get used to looking at these sorts of things. And we can do the same thing, which is use this linear combination of these sine Gaussian functions. In this case, it took a couple of more, but you can see how they represent different parts of the signal. The low frequency one is doing a good job of matching the in spiral. And then as the frequency goes up and the amplitude goes up, you need to change the shape of your basis functions to fit that part of the data. And then you need like a really high amplitude, really high frequency little piece at the very end, and then the signal goes away. And they actually start to destructively interfere with each other to squash down that wavelet power after the merger happens. Okay, so I can add all those together, and voila, it does a really nice job of fitting the binary black hole signal without having to use a template. I did not have to say, I think this is a binary black hole. It's just a good job fitting it. Yeah. Yeah.
Is that
It poses a problem if you're trying to decompose the data into sine Gaussians, but if you're just using them to make linear combinations to fit the thing, it's fine.
when you go to the process to like, maybe I'm jumping ahead on the lecture, but it's just, if you're going to process to the differential glitch from a signal, would the governing coefficients and parameters of that sign function be the thing that you draw that line on?
Almost. Okay, so this doesn't look very distinguishable from the glitch a few slides ago, unless you know what binary black holes look like. But the lever that you can use to do the model selection part is that gravitational waves show up at all of your detectors all at once, modulo the light travel time between detectors, and glitches don't. If they did, that would be bad. So if there's a glitch in one detector, there should not be a glitch at the same time with the same shape in another detector. So you should be able to veto glitches by demanding that glitches are not coherent across the network of detectors, but signals are. So I do my wavelet fit to a single channel, a single detector's data, and then I have additional parameters like where the thing is on the sky that help me figure out if it looks like this in Hanford, how should it appear in the Livingston data? And so the fact that these are correlated means that if I have a signal in one, I can predict what the signal will look like in the other. So I have one set of basis functions and then a few extra parameters that deal with the projection to figure out how to fit the data in two different detectors. If I was going to do this with the glitch model, I would need a sum of sine Gaussians in Hanford and then a totally independent sum of sine Gaussians in Livingston. Okay, that's going to be way more parameters than I needed to do sum of sine Gaussians in one and then projection onto the other. So the signal model will win. Yeah.
So when this is happening, how is, like,
It's not looking at one detector at a time, but ideally you've given in all of the detector data. So is it just kind of, I guess the whole point is it's exploring the space of trying to fit the signal and those projections to make the entire noise, the entire data set as Gaussian focused as possible.
Yeah. So what we're doing here is we're modeling everything and letting the data sort it out, or choosing a phenomenological basis. Okay, so now I have an insurance policy against the waveform models not being perfect. I'm using wavelets to cover non-stationarities. I'm using physics to project those onto the other detectors in the network if it's actually a gravitational wave instead of just noise. And we're going to continue ignoring the part about calibration. Nothing's perfect. So here's the model. So I have some number of spline coefficients that have a frequency and a power level, and then I interpolate between them to get the broadband part of the noise. I have some number of Lorentzians, which are parameterized by three numbers, frequency, amplitude, and Q factor, how wide it is. Those are going to deal with the lines. I have some number unknown of sine Gaussians that I'm going to use to fit glitches. Those have 5 parameters each, frequency, time, amplitude, quality factor, and phase. I also have some number of sine Gaussians that are going to fit signals, which have the same parameters for the shape of the sine Gaussian, and then these additional parameters that tell me how to do the projection. Or I can say, well, for my signal model, I'll actually use like a proper black hole waveform template. And we've thought about doing things like calibration, but I'm not going to get into that. So each one of these is its own transdimensional Markov chain Monte Carlo, because I have to figure out how many of these features to include in the data. And then there's an additional model selection step to decide if a feature in the data is better fit by the glitch model or the signal model. Okay, so now we're going to put it all together. So here's some data. This is real data that has a real signal and a real glitch on it. And you can see the transdimensional MCMC do its thing. So let's just be mesmerized. So the signal is in both the Hanford data and the Livingston data. There is a glitch in the Hanford data. So the glitch model is going to be in orange. The signal model is going to be in purple. This is another one of these black hole mergers. And on the left-hand side is the noise model. So you can see all these different spectral lines, and you can see the broadband parts are jiggling up and down. So some things to point out. When the video starts, here we go. There's orange in both channels. Because right away, the model thinks, oh, I see some excess power in Livingston. I see some excess power in Hanford. I'm going to fit that with the glitch model. So let's see if the video will start over again for us. So you can see the sort of orange come and go in the Livingston data, but then eventually you just get a better fit. You use less parameters. The model selection prefers using just signal wavelets instead of glitch wavelets to fit the common features in both. And so at the end part of the video, you just don't see any orange show up here at all. Another interesting thing to see is, especially here at low frequency, lines in the model sort of come and go. Sometimes you'll see a spike in the fit and sometimes you won't. And that's because the model selection just can't really decide if we should include a spike there or not. And so it sort of comes in and out. So the Bayes factor of whether or not there's like a spectral line at a few hertz is kind of up in the air. You can also see the spikes sort of changing in height. You can see the broadband part wiggling around. And so you just let this run for a while. It's mesmerizing. And then at the end, you can look at the sort of model selection results. So these histograms, these are the posterior distribution functions on the model. So here's the spline model. In the Hanford data in orange, the posterior was pretty tightly peaked around 22. So it really, really liked 22 spline coefficients in order to do the broadband part of the noise. The Livingston data was a little bit smoother. It only needed like 14 or 15 or so, but you can see there's a distribution there to the number of parameters. You can make the same sort of discussion about the number of lines in the Livingston data versus the Hanford data and the number of wavelets used to fit the glitches and the signal. So we said the glitch was in the Hanford data. So the glitch model peaks at like 2 or 3 wavelets. There was no glitch in the Livingston data. The glitch model in the Livingston data peaks at 0. Good job, model selection. And then you have some purple, some signal wavelets clearly sticking out at like 4 or 5 wavelets. So this is pretty strong evidence that there's something coherent in the data. And then you can make my favorite types of diagrams, which are showing the posterior distribution function on the feature that you're fitting in the data. So that if you squint, you can see that there's now a distribution of the PSD. So there's like a black line which marks the median, but then there's an envelope in gray showing you how much uncertainty you have in the PSD over that part of the data. And then the same thing goes for the signals, where you can see the purple is the median reconstructed signal, but then there's some fuzz around it for your uncertainty in the reconstruction, and same goes for the glitches. And you can see there's like a little hint of orange. It's not there in the median, but it is there in like the 90% credible intervals. It was tempted to include a wavelet in that low frequency part, but then ultimately the sort of median or the 50% credible interval just said, nope, there's nothing there. It's just all signal. Yeah.
All this signal that we don't know tomorrow, but regarding the actual gravitational signal, how do we convert those parameters that are basically frequencies and amplitude into the actual physical frequency?
So if you have an actual astrophysical model and you're confident in it, you can just use that instead of the wavelets. And so we do that as well. That's what most of the LIGO parameter estimation is done using actual, physical templates. But one of the things that you have to do is search for signals that you're not looking for. So in the LIGO parlance, these are called burst searches. I think you have a similar concept in pulsar timing. Oh, maybe those are just bursts of like mergers. I don't know. Anyway.
It's natural.
Okay. So if you only ever look for things that you know are there, you're only ever going to find things that you know are there. So these sorts of like, source agnostic methods are really there as an insurance policy against other kinds of transients. But if you have a bunch of gravitational wave transients, they just happen to be black hole mergers. I mean, you still want to run the pipeline on them. And then you can do things like you can compare the reconstructed waveforms using the wavelets to the templates and see if they overlap with each other. And we do this in a quantified way often to test whether or not the templates are doing a good job fitting the data. There are things that you can calculate, just like energy rise times that map to things like sizes of what the source must be. And you can compare those to things like the total mass of the binary. And so there are ways, they're sloppy, but there are ways to map just the reconstructed signal to something physical if you make some assumptions about the source.
Want to do this physical way? Would you still use transdimensional sound for, say, I don't know, testing the general seals, where you use different templates of the same model. But you let, for example, one model depend on a certain number of parameters and one with an addition one to see if you're degenerated with that.
Yeah, so if I go back a whole bunch, I think it's on here somewhere. So like here, we're using this generic signal model using these wavelets, but you could just swap that out and use something like a black hole merger. So masses, spins, orbital angular momentum, sky location, distance, and time, right? So this is something people in LIGO did a lot back in the day before we had detections to deal with, was argue about whether or not you should include things like spin in the model, because spin is not something that you measure very well, except for in a few cases. So here is where model selection can get you if you forget about that prior odds thing, okay? So let's say I'm going to do a model selection study to determine whether or not I've measured the spin. So a model where I've not included the spin parameters is a model where the spin is precisely 0 for each black hole. Find me an example in astrophysics where a black hole would have 0 angular momentum. Not very good. So the prior odds should include the spin, right? Because there's no way it's going to be exactly 0. So you can use this machinery to write papers about base factors of whether or not you've measured spin, but it's not actually, I think, all that useful because we know the spin is there. We know it's not 0. It'd be insane if it was 0. And then it turns out that spin couples with other parameters. So if you fix the spin to 0, you're underestimating the statistical error in other parameters like mass ratio, because they're actually correlated with each other. So here's a cautionary tale, where just because you can do a model selection study doesn't mean it's worth doing a model selection study, because we have really strong priors that there should be some non-zero spin. Even though it's not measured well, you should at least marginalize over your uncertainty.
If I may add to that?
Yeah.
There could be cases in which say you have inclination and that is degenerate with respect to another parameter.
Yeah, but we know it's inclined. Now, if someone came in and told you, I've observed this binary electromagnetically and I've measured the inclination to some nauseating accuracy, then sure, you can use that. But if all you have is the gravitational wave information alone, we don't know what the inclination is. So maybe it's generally something else. You could fix the distance and that therefore fixes the inclination, but you didn't know what the distance was either. So you just end up fooling yourself. Yeah.
Don't know if that parameter is not or not. Like, let's say you're testing a model that has a modular parameter, and probably 0, maybe not.
Right. So now testing GR is a different case, right? Because there 0 is a perfectly good answer. In fact, the prior should probably prefer 0 for non-GR parameters. So there, adding an additional parameter there and doing some model selection study does make sense. So it's just, you just have to think, you have to think beyond just the base factor part, just the likelihood ratio, and also consider what it means to assume one model versus another. And if you're okay with the physical implications of one model versus the other. Any other questions? Whoop, too far. Okay, so back to, I think that was it, yep. So back to this Hastings ratio that we've been talking about. Here's one more piece of intuition I'd like to build before we move on. Remember the prior of the new parameter lives up in the numerator, and the proposal for the new parameter lives down there in the denominator. So let's split those up into separate fractions, why not? Now, let's take the really simple case where the prior on this new parameter phi is just a uniform distribution over some range. Let's pretend phi is an angular parameter, so it's like 0 to 2 pi. Then the prior is then 1 over the range, right? Okay, so now there's something really instructive here. So ignore the part about the proposal distribution for a moment, okay? Now what you can see is that the likelihood for the more complex model lives in the numerator for the case where you're trying out this additional parameter. So you have more knobs to turn. You should be able to get a better fit of the data with those extra parameters. In the denominator, the thing that's preventing you from adding that additional parameter to the model, you have the lower value of the likelihood, but you also get help from this prior volume factor. So if you want to include an additional parameter, not only do you have to improve the likelihood, but you have to improve the likelihood by enough to overcome this extra volume that you're adding to the model. So have we ever heard of Occam's razor? Occam's razor says, a little bit oversimplistically, that the simpler model is always right. Here is a quantification of Occam's razor, which says, actually, how much is the simpler model always right? The simpler model is always right by the prior volume. So if you add a model parameter that has a big prior volume, you're going to be asking a lot of your likelihood to overcome it. This, my friends, is a slippery slope. Because if you get a base factor of like 2, you could say, well, what if I shrink the prior? Now the base factor gets bigger, right? Because I've just reduced the size of that penalty. And so then people squawk and say, see, a Bayesian model selection, it all depends on priors. You're right, it does. And if it's something so borderline that little changes in the prior give you different interpretation, then you might be over-interpreting these base factors, okay? The other thing to point out is that I think, nope, if your proposal distribution is that you're drawing from the prior, then these two terms cancel, and the reversible jump Markov chain Monte Carlo is just a likelihood ratio. Everyone thinks these things are really complicated. They sound really complicated. You can cook these up where they're really, really simple. I wouldn't suggest that as a production pipeline to be just using a draw from the prior for your transdimensional steps. But if you're trying to build one of these up from scratch and you want to start easy, you can just ignore all these bits and work on the mechanics of just adding and removing model parameters to your fit, and it's just a likelihood ratio. And then you have to start including these bits when you actually want to do a more efficient job of sampling. Okay, and then my last little bit about all of this is that these are horribly inefficient samplers, unless you do a really, really good job of designing the proposal distribution. I think you've already talked about this in the context of MCMC, where you need to use your domain expertise and some dark art to come up with proposal distributions to do a good job of sampling within parameter space. That is even worser in the transdimensional case, because in the transdimensional case, you're also fighting against this extra prior volume. So when you build these algorithms for real, to do like real inference problems, you have to spend a lot of time of thinking about how you're going to build these proposal distributions. So I'm going to show you 2 example proposal distributions that make this all work in the context of the, here in the LIGO example, and then I'll show you a LISA example as well. So again, this is yet another black hole merger in some LIGO data. Here shown, it's the same data, but shown in 4 different panels. Each one of these is a time frequency map. So you have time in the horizontal axis, you have frequency in the vertical axis. And if you know things about like wavelet decompositions, this is what you get if you do a wavelet decomposition of some data. You get a time frequency map. So when we want to do this, this reversible jump with these wavelets in the LIGO data, it's not just that we're adding 1 additional parameter, it's that we're adding 5 additional parameters. It's all the different parameters of the wavelet, the frequency, the time, the amplitude, the quality factor, and the phase. So that's a big volume that you have to overcome, so that you need to do a really good job of improving the likelihood, or else that proposal just never ever gets accepted. So we need to teach our algorithm really clever places to try introducing these wavelets in order for us to have any hope of mixing well to actually measure these base factors. So what we do is at different choices of this quality factor of how wide the wavelets are, we do different wavelet decompositions of the data and measure basically the excess power in each time frequency pixel at these different decompositions. So I do low Q decomposition, some medium Q decompositions, and a high Q decompositions. These are just like different knobs you can turn if you do a wavelet decomposition of some time series data. And then I can turn this into a proposal distribution by stacking all of these up into a cube. Now it's a 3-dimensional volume, and then normalizing the whole thing so that if I sum up all of the different cubes, it adds up to 1. And so now I have a probability distribution in this time frequency quality space, TFQ space. And I use that for my transdimensional samples so that I'm preferentially jumping into places where I have excess power in all of the different Q layers that I've done when I've done the decomposition. So if I use this as a proposal, my proposal says you should really try something out at about t equals 0.1 and about 64 hertz. That looks like a good spot. Was there a question brewing? Yeah.
Why this is really cool. I'm trying to understand why does the noise not get the same, like, scale, because if they're just like transformations of each other, I mean, maybe I'm thinking about this wrong, but like, shouldn't the noise, shouldn't like some noise segment also look especially bright in the other representations? I think I'm just a little confused why the signal remains bright, but noise looks very, it cancels itself out.
Yeah. So for each cue, so pick one layer, you can actually kind of see it. You can see the sides of the pixels. The pixels here look like little squares. The pixels up here look like rectangles. So you can imagine that it's like a little filter that's just going to pick out a little time frequency area, but they're not perfectly square, right? So they bleed off into different times and frequencies. And then you just integrate up all of the data over that little pixel, and that tells you what the value is. So the noise is constantly root ending itself inside of a pixel, but where you have signal, it is adding up coherently. Yeah. Okay, so this is like the central engine to getting our transdimensional samplers in the LIGO case with these wavelets working, is by doing these time frequency quality factor decompositions. So this requires a lot of pre-thought, right? You don't just turn on an RJMC and MC and hope it does the job. You have to really, really think about what the target distribution looks like and find a way, hopefully a data-driven way, where you're actually doing stuff to the data you're going to analyze to generate these proposal distributions so that your algorithm mixes in a human time span. Okay, and now, with not too much time remaining, is my favorite application, which is the Lisa Global Fit. I could go for weeks. I'm not going to go for weeks. I'm going to keep this one short. Yeah.
You're the headline this morning, or you're supporting that?
Well, I only have like 3 more slides because I knew this was the end. But, I can come back. So this picture is supposed to help you realize that the Lisa Global Fit is a real thing. So on the left-hand side, we have a time series of simulated Lisa data. It's 2 years worth of data, and it's color-coded by all the different source types. On the right-hand side is the power spectrum of that same data, again, color-coded by all the different source types. So what are the things to really point out? So the first thing you might notice is these really bright pink spikes. Those bright pink spikes are supermassive black hole mergers out to the arbitrarily large distances in the universe. So when you look at this, you're like, oh, cool, Lisa data analysis is easy. If all I care about are supermassive black hole mergers, I make a time series and I count the spikes. And that's true. But there's other cool stuff in there, like the purple is the signal from the Milky Way galaxy. So the Milky Way galaxy has something like 30 million-ish white dwarf binaries that we think are radiating in the Lisa band. That's a very significant contribution to the Lisa data. In fact, if you look at the power spectrum, the color doesn't show up so great. This blue is the instrument noise, and the purple is the galaxy. So at like 1 to like 5 millihertz, the galaxy is actually much, much louder than the instrument noise. So in LIGO, and to some extent in pulsar timing, what you're doing is trying to sift through noise to find signal. And in Lisa, what you're going to do is sift through signal to see if you can't see any noise to tell the instrument scientists how well the detector is working. Okay, the instrument performance is limited by the amount of gravitational wave signal there is coming from the galaxy, not from how well they build the detector at like 2 or 3 millihertz. Now you don't tell the engineers that, because then they don't build as good a detector between 2 or 3 millihertz, and we could be wrong. But odds are that Lisa is really just all signal. Okay, you might also notice that it's modulated. Do you know why it's modulated? Lisa is orbiting, yes, And gravitational waves are quadrupolar. And gravitational wave detectors have quadrupolar response. So the LISA satellites make a plane. You're more sensitive to things above and below the plane than you are things in the plane. Not perfectly, but by a factor of like 2-ish. And so as LISA orbits around, most of the galactic binaries are in the galactic center because most of the things in the galaxy are in the galactic center. And so when the galactic center is normal-ish to the plane of the detector, the galaxy is louder. And then when the detector moves and the galactic center is in the plane of the detector, it gets quieter. So you can see these modulations caused by LISA's orbital motion. And you can do things like use those modulations to learn about the relative fraction of signals in the disk versus the bulge versus the halo. Maybe it's super hard. Some other stuff to look at in here while we're at it, just because it's cool. This green blob is a bunch of extreme mass ratio inspirals all added together. These are like one of the hot science cases for LISA. These are small black holes orbiting around really big black holes. You can tell that they are super duper quiet compared to all of the other signals in there, which means to find extreme mass ratio inspirals, you need really, really precise templates, really, really precise predictions of what the signal looks like, and then very sensitive search algorithms to find them. I would say technologically, this is the hardest part of LISA data analysis, is finding MREs. So if you are looking for a really important project for LISA someday, you could think about coming up with algorithms to find MREs. Some other stuff, these orange, light yellow spikes are the black hole mergers that LIGO sees, but way before LIGO sees them. So they're just orbiting around each other at long orbital periods so that LISA observes them, but then gravitational waves shrink the orbit and speed up the period. And so they eventually migrate out of the LISA band and like 10 to 1,000 years later merge in the LIGO band. So that's cute. And then the last thing to point out are these orange spikes. These are like 24 or so white dwarf binaries in our galaxy that we have already discovered using boring old photons that we know we will observe with LISA once LISA turns on. Some of them are really bright. One of them, the highest frequency one, HM Cancri, we think will be detectable by LISA within like a week. So we'll still be commissioning LISA and we'll already have gravitational wave sources from our galaxy that we'll be contending with. And if our models are right, there are way more out there for us to find right away. HM Cancri is probably just the tip of the iceberg for these high mass short period binaries. Okay, so that's all the good news. The bad news is that you have to then separate all of these different sources to figure out how many white dwarf binaries there are, how many MREs there are, how many black hole mergers there are, and characterize their parameters. And you can't do them one at a time because they're all sitting on top of each other. So this is the model selection problem from hell, is to sort out all of these different sources that are all sitting on top of each other to properly characterize the numbers of the different source classes and the parameters of those sources. So here, if you do one of these like transdimensional Markov chain Monte Carlo things, what you end up with is a probabilistic catalog instead of just a list of LISA sources. So here's just a very tiny little segment of LISA frequency band. So this goes from 3.98 millihertz to 4.005 millihertz, okay? So if I go back to this plot, that's just like a slice right here. Okay, and the way we do the analysis is we chop it up into shorter frequency segments, but then analyze them coherently, don't worry. And so you can see, if your question is how many galactic binaries are there between 3.9801 millihertz and 3.98433 millihertz, the answer is 12 or 13, right? The answer is not 12. It's an answer with error bars because we use these transdimensional samplers. Look at this. This is a hot mess. Between 3.98433 and 3.98857, they're like anywhere between like 1 and 10. Okay, there's a lot of uncertainty in that little frequency range about how many white dwarf binaries there are. Imagine figuring out how to serve this catalog to the research community. You'd need like a whole science center to figure out how to do this. Okay, and you can just keep going in frequency and watch as your catalog just has these fluctuating error bars as you go. And again, that's just a slice, and we have to do this over many decades in frequency. This is a big opportunity. Okay, so just like I said, you got to use a lot of domain expertise to build these really clever proposal distributions. I'll just gloss over my personal favorite one right now for the white dwarf binaries. So here's an example of a very high mass short period binary in some LISA data all the way up at like 18 millihertz. So according to some population synthesis models, these are like the highest mass shortest period binaries that we'll see. If these exist, we'll be able to see them in like the Magellanic Clouds too. That's pretty cool. The trick is then to try to fit this very, very loud signal with just a single template, because we know it's just a single signal because we simulated the data. And it's very tempting for this transdimensional sampler to use lots of different templates, lots of different white dwarf binary waveforms to try to soak up all this excess power, because there's so much excess power. There are lots of like secondary maxima in the likelihood. So we've over the years devised similar to the TFQ proposal, where we take that like slice of frequency, and then we use template waveforms against the data at different places on the sky. Just grid up the sky and calculate the waveform at all these different places on the sky, and take the inner product of the waveform with the data, and then do some clever maximization stuff to build a heat map. Now, instead of T, F, and Q, like we did with the wavelets, it's in frequency and RA and DEC, or galactic latitude, galactic longitude, whatever your favorite sky location parameters are. So you can make like a heat map at a particular frequency over the sky, and then as you scan through in frequency, you can see hotspots show up and then go away. And it just turns out that 18.3 is at about the right frequency for this binary, and so you see this like really hot spot at this place near the galactic plane. Well, that makes sense because these are all galactic sources, so that's probably where it is. So then when you're trying in your reversible jump Markov chain to just add and remove white dwarf binaries from the fit, you're being parsimonious about trying to add them in places where the data already thinks there's a good one there, but then you have all the nice detailed bounds rules to make sure that you don't bias yourself. And so then to finish is an animation of how this works. So on the right is the sky location. The color is the relative probability for this distribution. And then you can see its scan in frequency. And as it goes over a spike where a signal is, you can see that you get a lot of hotspots on the sky to go try out. But then when it gets far away from the signal where there's just noise, then there's just not all that much interest to go look there. And so our proposal distributions, one of our proposal distributions is to use these kinds of sky maps so that it's preferentially trying out places where we think there's signal. Let's watch it again. There it goes scanning. So there's just noise, so it's just kind of flat. And then there's a bunch of signals sitting here at about 7.7 millihertz. And so once the scan gets to those frequencies, all of a sudden it's like, oh baby, try that one out. That's a good spot. And then it's noisy for a while, so it's not so interested. And so then you aren't wasting so much time proposing places where the data have already told you that there's not a lot of interest. Okay, we'll let it finish. It finished. Okay, that's it. I hope that you have more questions, but that's all I have for slides. So what other questions do you have about, what was it, advanced sampling methods?
Well, there were a lot of questions about sugar reform. You probably answered this already, of course, I'm gonna ask it anyways. What happens when those parameters aren't independent, like, and you start having more complicated ratios for this, extra parameter model?
Yep. So this is where the domain expertise has to come in, right? So if I know that I have some highly correlated parameters, then I'm best off my proposal distributions leveraging that and choosing those parameters in a correlated way. But all the machinery stays the same. It's just that the proposal distributions end up being joint distributions on multiple parameters instead of a product of single distributions on single parameters. Or you can say, well, I know they're correlated, but it's kind of hard to code this up. And so I'm just going to hit it with a bigger hammer and accept that the mixing will be inefficient. And you just have to take many, many trials before you end up with something accepted. So you can just heat up the planet a little more by using a bigger computer and just have to thin the output to get that autocorrelation down in the chain. Or you can spend some time trying to engineer a really clever proposal. And in my experience, it's usually a pretty good race, right? Between just hit it with a bigger hammer and have less efficiency versus spend a couple of months coming up with something more efficient. It's a balance. Yeah.
Can you explain why most tend to I'm quite follow the root net?
This is was on, organic library.
Okay, so imagine you have just white noise. And then you're going to sum up that white noise, so it's just Gaussian random draws with zero mean unit variance. And if you add it up, the expectation value of the sum is the square root of n, right? If you have something coherent, like a sine wave, and you use a template, so you multiply the sine wave with the data, and then you add those up, then it sums to a much larger value. You're not getting all those little cancellations as you're adding it up, right? Okay, so the signal, when we're doing the time frequency maps, is well represented by these sine Gaussians. So I know that if I take a sine Gaussian and I just keep like running it over the data, it will eventually sum up to a larger value than just square root of n when it finds something that kind of looks like a sine Gaussian. And so that'll be like a hotspot in the map. But if that filter is just sitting over a bunch of noise, then and I add up over that filter, then I just get square root of n type fluctuations. So as I do this over the whole data cube, the places where it's just noise grow like the size of the data cube. The places where there's signal grow faster because they're ringing off of the basis function that I'm using. That make sense? Okay.
You have a nested model where any additional parameter, if you set it to 0, then that second model becomes the first one. Should you, if you're using that example, should you open your prior volume to an setting that parameter equal to 0?
Oh, that's actually it's a very nuanced question. Not always. So let's pretend that my model is there a white dwarf binary or not in this chunk of Lisa data? Then those models are nested because the version of the model where there is not a white dwarf binary is the same as a model where the white dwarf binary's amplitude is 0 or its distance is infinity. You can choose whichever you want, right? So in that case, if I feed just noise to that algorithm, the Bayes factor for is there signal or not will never tell me that there is not signal. It will tell me, there might be noise, there might be a bunch of signals in there with 0 amplitude. Okay, for me, a signal with 0 amplitude is noise. And so if I'm doing a model selection where I'm trying to use that for detection, I should probably choose a prior on my signal parameters so that it's not nested with the noise case so that I can use my Bayes factor to help me distinguish. So in this Lisa algorithm, where we're trying to fit maybe 10,000 binaries, we don't want to have all this junk in our sampling of like millions of binaries with 0 amplitude. So we have a minimum amplitude, it's a minimum signal to noise for a binary in our model. It has to have a signal noise greater than something like 7. It's probably 5, it's probably more conservative than that. So then if the Bayes factor comes back, if the data does not contain a signal with signal to noise of 5 in it, then the Bayes factor will come back and say, this looks like noise. But for the case where you're just trying to measure like a non-GR parameter, we don't really have a good reason to set a prior on the non-GR parameter. We have a good reason to set a prior on what we think is detectable. So in the testing GR case, I would argue that you should include the GR case in the non-GR model, and then a prior that's, or a Bayes factor that's sort of up in the air between the two. Well, you know that the prior for the model is going to come in and say, well, just take GR. Does that make sense?
Yeah, it does. In the case where I'm going to go ahead and plus periodic signal, and there's 3 periodic parameters, I'm having 3 dimensions prior.
Yep.
So even if the amplitude is 0, wouldn't my evidence for the periodic model still be parallel?
Oh, I'm so glad you asked. I seeded this question. No, I didn't. So the Bayes factor, it's easier to just say it than try to find an equation where I didn't actually prepare it. So if the posterior samples are filling up the prior, that penalty term actually gets canceled. So the Occam factor comes in if the parameters are constrained, not just if you have extra parameters. So if I need an extra parameter and I need to constrain it to a particular value that's a lot smaller than its prior, then that's where that penalty factor comes in. So the actual like Occam factor is the ratio between the posterior volume and the prior volume for that extra parameter. So if you have 3 parameters to fit a periodic signal, but one of them is the amplitude and you allow the amplitude to go to 0, then your other parameters like phase and frequency or whatever are just going to fill up their prior, right? Because there's nothing to stop arbitrary phase if you have amplitude 0, whatever. And so all those terms end up canceling, and the model selection doesn't pay a penalty for those additional parameters. So the penalty you pay is not just for extra parameters, it's for extra constrained parameters. Okay. Anything else?
All right, well, he's here all day.
I'm here all day. Yeah, I look forward to lots of papers about reversible jump.
All right, take a break, and then you know the rest of the day is free hack time. This is your opportunity to make that final push on many projects, get some slides together, decide how you want to present things tomorrow. It'll be, I think we should aim for 15 minutes maximum for each team, allow for a few minutes for questions. And I think we can start a little bit later tomorrow with 10 a.m. And we round up the goal of presentation 5 and much less. Okay, so free hack time. Let the people in the room know if you need some help, if you want to bounce some ideas around about a mini project. Otherwise, we've also got an additional expert in the room.
Thank you very much. My pleasure. How many are local and how many are external?
It's like, just 16, visiting, and then about.
Yeah.
Hey.
Is there like a good reference source, that goes into a lot of detail of all these sampling methods that you like best?
So the LIGO example, the algorithm is called Bayes-wave, and there are only 2 or 3 papers that have Bayes-wave in the name,
Okay.
and they're all good references. Go in order, time order.
This is for the RGMCMC.
No,
Oh, this is for specifically the.
yeah,
library.
because in order to get these things to work requires so much special sauce for your particular problem
Yeah.
that there aren't really good, just generic, right? The generic RJMCMC papers are written by mathematicians about proving that RJMCMC works, which if you're curious if it actually like does all the statistics that they say it does, are a useful read, but for like an application, it's just mathematician gobbledygook. Right?
Is anyone else using this other than LIGO right now?
Lisa?
Yeah, LIGO, Lisa.
Where else have transdimensional? So I know, it's a good question. Who else is really into this sort of stuff? I would bet Gaia has some model selection going on. Gaia is a astrometry mission.
Yeah,
Familiar?
yeah.
We borrowed a lot of this Bayesian stuff from the CMB community, the cosmologists. That they have fewer models that they have to contend with, so they probably don't do a lot of transdimensional sampling. They probably just do like model A, model B, model C, do some Bayes factors, kind of like what nanograph has done. Yeah, it's a good question. Let me keep thinking about that, if I can think of a good example outside of the gravitational wave world.
Could I pick your brain on an idea for an application?
Yeah.
Basically, it's scripting me. So I work on hierarchical modeling, particular noise models. which could be due to a couple of reasons. And I'm reading a paper and I'll put out, drafting and doing a Bayesian analysis on different sources. And I was wondering, kind of, that it is a model selection problem. We got model this red noise that's, in an asteroid belt, is like super fluid. The multiple forces going on at the same time. That sounds like what this method is designed to do.
Yeah.
One. Maybe this is just gonna be repeating something in a physics. What really distinguishes the transdimensional sampling from doing normal model selection with Bayes factors?
So normal model selection of Bayes factors means you discretely go through one model, do an analysis, calculate an evidence. Go to your next model, do analysis, calculate your evidence. Do that for all of the models you want to consider, and then compare the evidences. The transdimensional sampling means that you are moving between models as part of the sampling to begin with, instead of just going one model to the other.
Yeah.
The advantage of it is that if one model is really bad, then you don't waste any time because the sampling just doesn't like that model. Right? So if you have, what were your three examples?
There's four different sources. There's asteroid belts, there are magnetosphere state switches, there is instability in the pulse profile, and there are superfluid vortexes.
Okay, so let's pretend one of those is really bad, like asteroids. Let's say asteroids is a terrible fit. If you're gonna just discretely go from one model to the next, then you've got to do all that work on the asteroid model and then find out it's dead on arrival, right? If you're doing a transdimensional problem where you're sampling between asteroid and superfluid, I think those were two of the choices, right? And superfluid's a really good fit and asteroid's a really bad fit. It just never bothers with the asteroid model.
If you were to include, joint models where the signal might be described by some mixture of
Right.
and superfluid.
Right, so then if it's a continuous model space, then transdimensional is the only game in town.
Then I think I should learn these as well. Because the other paper I was reading them is great source.
Right, now, I guess what you could do is you could have them be, what is it? Asteroid and superfluid.
Yeah.
And you could have those just be fixed on at the same time in your model.
Yeah.
And then just like a weight parameter that says it's more of one or more of the other. And if one of those models is really bad, then the weight parameter would just be like 0 for that one and 1 for the other one. So that's one way to do it. Then your sampler is like sampling over all of these parameters and then just getting whacked by this 0. So it's gonna make the sampling less efficient, even though a big part of the model isn't actually contributing anything to the likelihood. Going into that way.
And that would be in the event like you have something that was very much one or the other.
Yeah,
So if it was definitely superfluid, that the fact that the evidence that like the sample mass did not confer an asteroid belt would just emerge.
yeah, it would stop using that model. So one way it's a piece of jargon is importance sampling, where the algorithm only spends time sampling places in parameter space or models that are important to the fit. It doesn't waste its time doing evaluations in a place that's a terrible fit, either in parameter space, right? If you run an MCMC, it's able to sample the whole prior, but it doesn't. It just samples around where the likelihood is, doesn't waste its time over in prior because the likelihood's bad. Model selection's the same, but now, across dimensions as well. It's just not going to waste its time exploring bad models. If you have a bunch of discrete models, you need to run each one and then compare. You might find like the Bayes factor for one to the other is like a gazillion to 1. Well, you just wasted a whole bunch of time doing the one that's downweighted by a factor of a gazillion.
If you have two models are simultaneously conferred, say one is slightly more than the other, as with your transdimensional model.
Yep.
Would you be able to? Would the output of the transdimensional model Be able to tell you about the differences. What I'm trying to get at is, can it characterize a posterior spectral index in HB?
Yes, so it's gone. So it's doing the parameter estimation. So when you set these things up, just like in a regular sampling, you'll have like a cocktail of different proposals. So you'll try some kind of draws and some others to do the parameter estimation. A transdimensional sampler, you'll have some within model moves. So your asteroid model is updating its parameters. And then every once in a while, it's like, oh, well, let's also try adding superfluid, or let's switch from asteroid to superfluid. And then you can update those parameters for a while. So you get the model selection and the parameter estimation out of the same analysis. Which is different from nested sampling, where you have to do the model selection part and then do more work to get parameters. Or just like a straight MCMC, get parameter estimation and then do more work to get evidence. RJMCMC wraps that up into one.
I think this sounds very productive.
Now, the other thing, so for the LISA case, the white dwarf binary case,
Yeah.
and for the LIGO case where we're doing this linear combination, the number of different model combinations is just impossible to deal with discretely. Right, we have maybe 10,000 white dwarf binaries, maybe 9,000, maybe 12,000. I can't run the 9,000 version, the 9,001 version, the 9,002 version, and then do Bayes factors after the fact. So when you have many, many different combinations of possible models, and doing it just like Bayes factor style, just very quickly becomes impossible because the combinatoric skill.
You just mentioned like in say the one less tiny slice of signal review, 100 white dwarf binaries from specific memories. Like what you guys are doing with this is differentiating between those
Yeah.
characters. Okay, I will likely have more questions on this as I go in.
Okay,
Would it be okay if I emailed you since
Sure.
I have no idea if it's weeks, months, or
Yeah.
like a while? Okay, my name is Martine.
Okay.
As I.
my name is Tyson. I have terrible email discipline.
Yeah,
So I strongly believe in natural selection in my inbox. So if you email me and you don't hear anything back, just keep going. Just keep emailing.
hey,
Yes, exactly, exactly.
okay, thank you so much.
Welcome. So,
Hi, I really enjoyed your talk, by the way. I was, sorry, I'm a little bit, I don't know too much about how these, perhaps what is the Q in the, when you're doing the hierarchical, base time?
that's the proposal
That's
distribution.
proposed.
Yeah, so that's how you're generating new values.
So that's the prior, that's just the prior, am I right?
Nope, the prior, well, it could be.
Yeah.
So the prior is something that you write down before you've done any work. Right.
Mhm.
And then the proposal distribution is how you're going to generate new samples. The prior that you write down shows up in the Bayes' theorem. It affects the results.
Right.
The proposal does not affect the results. It affects how quickly you get the results. A good proposal means you get there more efficiently.
So did we just cancel out the priors when we're writing out the distance ratio?
If the proposal, if you choose your proposal distribution to be draws from the prior.
Yeah.
Then those things all cancel,
Mhm.
and then it's just likelihood ratio. Right, but that's just a trick of knowing that if I make my proposal be this function, it'll cancel this other function in this ratio, and I don't have to calculate those things anymore. It's not a good way to go for actual efficiency, but it's a good start when you're like trying to build one of these up from scratch.
And why were the proposal distributions flipped on the top and bottom? You said that they're,
So this was probably in either Alexandra or Kyle's lecture from earlier about MCMC. But the short answer is, you want the statistical condition that you're trying to maintain is called detailed balance, which means that if I take one sample in the chain and then another sample in the chain, I'm equally as likely to go from A to B as I was from going from B to A. There's no like direction in the samples. They're not sorted in any sort of way. To go from A to B, you have to propose a new location. And your proposing doesn't have to be symmetrical. So I can just say always, jump to a higher value 2/3 of the time and to a lower value 1/3 of the time.
Right.
I don't know why you would do that, but you could do that. So that means you're preferentially moving to a higher value. So then you want that in the denominator to say, if I'm really wanting to go uphill, then this thing in the denominator is gonna put pressure on me to go down. So they end up, now, there's like a way to derive it instead of just
Yeah.
like say it should go, it should be flipped. But the reason it ends up being flipped is so that it's basically, it's like a headwind. The more you try to move in one direction, the more it pushes in the other direction.
And in the HMC, in the HMCMC, why is it really important to know your initial position as opposed to the momentum that you're going and the direction that you're going?
So
Like,
yeah, so the position is the thing that matters. That's like a set of samples
Yeah.
from your posterior. And then you invent this idea of momentum and use Hamilton's equations to, if you give it a kick, to see how far it rolls and where. And that's a much more efficient proposal than just trying to figure out like little steps in one direction or little steps in the other. So you just like let the gradients of the likelihood decide, if I kick it in one direction, how far it goes. I let it roll for a while and then stop and say, okay, that's my proposal. So an HMC is basically a really fancy proposal distribution for an
Okay.
MCMC. And it's, instead of you having to build in knowledge about the shape of the distribution, it's using gradients of it, it's using derivatives
Yeah.
of the thing to figure out which directions it should go. The
Okay.
downside is it's really expensive and can be like numerically unstable trying to do all those derivatives.
Okay. Perfect. That's what I have so far. Thank you
Alright.
so much.
Yeah, no problem. Like pick your brain about what you like. Yeah. Oh, okay. Yeah, are you gonna fight that? Wait. Oh. Someday we're
Like you would be reading.
No, no, you got before
So, yeah.
Got it by. Yeah. Well, you said you were on there. Right, so that's like, oh. Two. Yeah. Right. So I just left it on. And 2 days ago, I came back to my apartment building. And I found it, parking space on the ground. And I was like, oh my gosh, someone idiot carrying it all the way down the stairs and tried to ride it. And they're like, no, taking this. And I was like, yeah, like, someone, like, that is strange. In the sense, yeah. It's not so, yeah. Yes, yeah, no, my partner has also said, no use by, so if you have to, if you want to, you have to get rid of it. Yeah.
I did, yeah. I don't wanna interrupt. but- Yeah. We actually, I brought this up in a meeting one time, and we didn't come to. It was about that, but you should let me consider zero balance. Right, yes, I'm sorry, I'm in Steve Group, I should say. Chris here, yes.
Hi.
Hey. Yeah. I search periodically on LinkedIn. Red noise plus period. And I think that's exactly. Initially, I've always let the amplitude go to zero, because I figured even at that time zero, like you would match perfectly with that additional prior for a while. Because in the intervals there, likelihood of time to the high theta, and I just. I did it here. Dimensions, that value that now. Five dimensions. That's where. You're saying. It's not just. It's how much. At A equals zero, it's not singular, so F in phase, whatever they want. So that doesn't. So. I should now I did
So I just downloaded that.
You said in the lower range that I should let it go here, it should just be conditional on SNR.
And they're
Actually,
actually
to accept the interest rate, yeah.
It's a capital.
So.
So that's why you have spits out. Empire. Mine spit out. So that might come. You can have, it's behavior, right, so I'm figuring out the. I could, but I'm also trying to figure out, yeah. So I'm trying to figure out.
A lot of waveforms that I can stress, that there's nothing like.
Well, I'm trying to figure out why,
Don't worry.
If the.
But in this example, probably not watching that.
Yeah.
You gotta do both these sort of things, and we don't, I have, I would say, the long, it's in kind of, you know, just not internally, you have base kind of thousands, where thousands, right? Yeah, that could be houses that they don't do that.
Yeah, like, in this.
The question I had was about, well, the two different detectors should have the same signal, different ways. Is that the case where you're looking at two data streams which should have the same signal, but different noises? Is that an easier problem if the noise is shared and correlated between the bands? Between the two different detectors?
It's variable.
You have to be able to separate.
Very
simple. Well, if it's not very old, Lisa, I'm also way this is close to choose that. So. It's dual matrix, which is one of them. And. You think about. So. A transfer function, the thing that they affect it, different. Transfer function of a piece of factory or. But. I don't think it's just that. Transfer function. One, that is, yeah, version of it, at least, not like this.
And.
Right.
Yeah, I guess you're.
Yeah, I think that might be useful.
Yeah, doable, more work to make sure.
So, yeah.
Yeah.
Well, you're not.
Not you, right?
Yeah. And the interesting thing is that the true, so if you have a red visualization of the G band that you observe on the R band, it's just like we say, a convolution. Red visualization. It can be represented as a function, and it's a function of things like simulation of the AGN disk.
And.
Yes, so in that case, where in the noise correlation of information follows, is it, do you think that would have value?
Yeah.
Yeah.
More data than never less.
And. The next year.
Oh, my gosh. This might not be forward. You, there is a number things. It's many times what they did. These are closed. You're
Yeah, thank you. I think that's all I have.
Okay.
I have to do some status.
And then on top of that is.
But not when you hear.
Where it's.
Every year's interesting. I just come from periodic research, just way too aggressive means. And I applied here. I basically, and Jeff run up. So, yeah, that's, I'm trying to get into.
Yeah, I assume that they would fit for that.
I mean, this is going to be, I feel like I have. To choose the allows it freedom. Many groups of three to four. Single source localization, really is different, using like Fisher bubbles and active VIPER. But there's really minimum other like single source.
Like if I say, like I guess maybe on the table,
It's just like blood. Like it seems impossible to approach it. So let's go like it might be a way to program. Even though I don't know, it's obvious, or it might be.
We have a similar. That's your.
Yes, I've heard of
There has been some. That's. Purely, you do. Have some project.
Yeah.
No, they're.
So the idea, you guys will come up with project, like data challenges that you guys anticipate. There's
Some things that we know we need that we don't. Really, I'm.
What's an example?
Well, so that would be like, hey, I had an idea of like doing that. Right, and another thing, hey, actually, you're trying to sign your trust for a study. Yeah, think about it.
All right.
Yeah, that's fine. Yeah, so it's supposed to be a short, bring your own projects. Yeah. But again, I'm sure more people will like it.
This is the.
There were like large people. Everyone's on for. But. Yeah, it's like overall. Period. So we change the power. We should create games. Here. Yeah, I can go back and. Really time on. Yes.
Like years, the next year, where the oldest one.
Sign. I don't want either. Yeah, well, I got it. What's all that? So if we use that.
You'll see me do a tendential switch. That's right, yeah.
Yeah.